Okay, so today what we're going to talk about is this idea in chemistry of radioactivity. Radioactivity. Okay. So if we think about like what is radioactivity? So the official definition of radioactivity is this here. So radioactivity is defined as the spontaneous breaking up of certain unstable nuclei accompanied by the emission of radiation. So really to kind of understand this, we have to take a look at the atom, and we need to look in the middle of the atom or within the nucleus of the atom. So what we have here, okay, we have the ability to make up different atoms. Now, if we think about the nucleus of the atom, so we have these two subatomic particles. You have protons and you have neutrons. Protons are positively charged and neutrons are neutral. So what we can do is we can actually build up an atom. Now, what distinguishes one atom from a number is the number of protons within the nucleus. So what we can do here is if we have a look at this, okay, and this here to just indicate the mass. So if we have one proton, for example, if we have an atom that has one proton in the nucleus, it's hydrogen. If we have an atom that has two protons, it's helium. If we have three, it's lithium. If it's four, we have beryllium. Five, we have boron. And if we have six carbons within the middle, it's known as carbon. Okay. Now each neutron carries a mass of one. Okay, so if we've each proton carries a mass of one. If we've six protons, then we have a mass of six. Now we can see here that six protons in the nucleus on its own like this is pretty unstable. So what we have to counterbalance that, we have neutrons. So again, so if we add these neutrons have a mass of one, so we can see as we add the neutrons, the mass here increases. So if we can see up here, we have six protons, we need to have six neutrons to to counterbalance that. So we can see here now that we have six neutrons within the nucleus. So we have six protons and six neutrons. And we can see now that the nucleus of this atom of carbon is pretty stable. And this is what's known as carbon-12. Now, what you can have is you can have isotopes, and isotopes are atoms like carbon, for example, that have more neutrons than it. Like so, this, for example, this would be a stable version of carbon. It has six protons and six neutrons. Now, carbon can have more neutrons, and it'll still be a carbon atom. So, for example, if we put in another neutron here, so we have carbon 13, okay, what's known as carbon 13, and that's an isotope of carbon. And then we have, if we put in one more, we have what's known as carbon 14. And we can see here that the nucleus of carbon 14 is quite unstable. And you can see this here. So it's kind of moving about. Now, what happens is, in relation to radioactivity, this unstable structure, it starts to break down. And when it starts to break down, what it does is it emits energy, or it can emit other particles as well, in order to regain, let's say, and lose. Basically, what it wants to do is it wants to lose one of these neutrons and come back to a stable configuration, or it might even lose protons as well. So this is this is what drives radioactivity, these unstable nucleuses within atoms. And we've all different atoms that have unstable nuclei. But again, carbon 14, now this happens in a very predictable way in relation to the breakdown and the emission of this energy and particles from the nucleus of an unstable atom. And that's the basis of carbon 14 dating, which I'm not going to go into any detail in this lesson, but it's just to kind of introduce like where radioactivity comes from. So basically the nuclei of atoms of every element, except like some simple isotopes of hydrogen, they contain they contain these neutrons as well as protons. And for the nucleus to be stable, it needs to contain a suitable ratio of protons to neutrons. Okay, so if the ratio is out of balance, like we can see here, we've six protons and we have 1, 2, 3, 4, 5, 6, 7, 8 neutrons. This ratio is out of balance, and as a result of that, the nucleus is out of balance and it's unstable. So if the correct ratio is not there, the nucleus of the atom is going to be unstable. And what's going to happen is this nucleus will start to degenerate, and it'll throw out fragments and or energy in an effort to achieve a stable ratio. So it wants to get rid of parts of the nucleus in order to maintain a stable nucleus. So this brings us back then. So this is what we mean by radioactivity. So radioactivity then, as we say, is defined as the spontaneous breaking down. Now this is important as well. So it just spontaneously happens. It doesn't need any external energy coming in to help it happen. It's just going to happen spontaneously. So it's the breaking up of unstable nuclei, okay, and it's relating to the nucleus of the atom, and it's accompanied by the emission of radiation. So essentially, you have this nucleus. So imagine this is your nucleus. It's made up of lots of protons and neutrons. It's quite unstable. So it's unstable, let's say, because the number of protons and the number of neutrons are not in the correct ratio. And as a result of this instability, it's going to emit radiation. So it's going to emit radiation. So this radiation is going to be emitted, and what it's trying to do in order, when it's doing that, emitting this radiation, the nucleus is trying to become stable. So it's trying to stabilize and become a stable nucleus. So it's trying to achieve stability. Now, if we think, so what I want to kind of talk about is, how did scientists come about and discover this spontaneous process of radioactivity? So scientists knew around the time that radioactivity was discovered, so scientists knew there were certain elements. Like if we take uranium, for example, so imagine this is uranium here. And they knew that, for example, when it was left out of the sun, so uranium absorbed sunlight, okay, or some of the radiation from, so UV radiation, for example, from the sun. So what it will do is it'll absorb this UV light, and then it'll emit it out. So you have different uranium compounds like this. So basically it would absorb, if you leave it out in light, for example, it'll absorb the light, and then what will happen is it'll give off this radiation. So if we take, like, for example, here we have glass that has compounds of uranium inside it, and we can see that it fluoresces or phosphoresces. It gives off, it absorbs energy, it can store that energy, and then it can emit it then as another form of radiation or light, as we see here. And that's, so you get this kind of effect, this luminescence, or this emitting of radiation. Now what scientists knew was that for this to happen, for these elements such as uranium to give off this luminescence, there had to be an external source of energy. So you could essentially kind of charge them up, if you like, with the energy from the sun, and then it'll give off this radiation. And that's kind of was understood, and it was a phenomenon that was observed by scientists as well. Now we have this guy here, Henry Becquerel. Now what he was interested in doing was, at the time, scientists were looking at what are known as X-rays. So it was a radiation that was given off, and it was given off, for example, when materials were energized, like, for example, when they're energized with light, these X-rays were given off. So what this guy Henry was interested in doing was, he wanted to see if you took uranium and you used different uranium salts, so they're compounds that contain salts that contain uranium. He wanted to see within this, so when you charged up the uranium compounds like this, these salt crystals of uranium, and it gives off this energy. What he was interested in doing is, he wanted to see, was there X-rays within this radiation here. So they knew about the radiation, okay, but what he was interested in doing, he was interested in finding out whether X-rays were given off, when, for example, uranium salts were charged up, if you like, by the sun. And roughly, like, just to kind of put it into context when this happened, so this was roughly around 1896. 1896. So it was around in the 1800s. So what he done was he took crystals of uranium, like so. Okay, so he had this uranium crystals. He exposed them to the light. Okay, and then what he done was he put them on. So if you take, let's say, so imagine this here is photographic paper. So photographic paper. So he had this photographic paper, and he charged up the salt crystals, let's say, of uranium, and then he put, imagine these charged uranium particles are here like this, and then he covered this, he wrapped it then to stop any sunlight from getting in. So he wrapped it up and he let the plate develop. So the first thing he done was he exposed this uranium salts to the sun, and he put them on a photographic paper, and then he wrapped it up, let's say, in a cloth. And then what happened was, so you get this kind of effect here. What would happen is the photographic paper would absorb some of the energy coming off the crystals, and you would get the development of these spots, these dark spots that related to the crystals. So what he thought then was happening was he thought that the absorbed energy from the sun, so that this absorbed energy from the sun was being released by the uranium compound in the form of X-rays. So he thought that, so you charge up the uranium crystals, you put them in, and you cover them up like this, and then you get these plates, these photographic plates that get developed. And he thought that the absorbed energy from the sun was being released then as X-rays, and it was developing the plates. So that's what he actually thought was happening, and that's what he thought was causing these images on the plates. So this is kind of like what he done. So instead of just going out and experimenting and doing this once, he went out and he decided to try this experiment out again at a later stage. So what he done was he went then and he set up the experiment again, but because the weather was really bad and he had an overcast day, so it's pretty bad. It was overcast, so the clouds were blocking the sun. So basically, you weren't getting as much radiation that was getting through. So he basically at the time he was unable to use the sun as an energy source for his experiment. So because on that particular day it was overcast, the sun, he wasn't able to use it to charge up his uranium salts. So he decided then just to give up on the experiment. And what he actually done was he put his wrapped photographic plates in a darkened drawer with some of the crystals of uranium. So basically he just gave up on it, and he took, so these were, let's say, so he would have had a plate similar to this, and he had crystals of uranium on it, but the crystals hadn't been, because it was overcast, he wasn't able to get the sun. So he had these crystals wrapped up, and he just basically he put them into a drawer. So he put them in a drawer, and he closed the drawer, so obviously it was in a darkened space, and he left this photographic paper with some of the crystals of uranium inside the drawer, inside in the darkened room, and he went off and just never thought anything about it. And he left them in here like this for a couple of days. And then what happened is, for whatever reason, he decided to come back, and it was luck and it was chance. And sometimes a lot of discoveries that happen within science just happen because of just blind luck, basically. So what happened, for whatever reason, he decided to develop the plates, And the results, what he found was that the results were identical to when the crystals had been exposed to sunlight. So what he was doing was he was getting this exact same effect happening, even though the crystals had not been, let's say, exposed to the sun and they had been put away in a darkened drawer. He found that this same effect was happening. So these this photographic paper was getting developed, and he was getting the shape of the crystals, or he was getting, like, basically where the uranium salt was on the paper, he was getting the development of the paper like so, and he was getting these dark spots within the paper. And this is the actual photographic paper that he used, and he developed a picture of it. So what this meant was that these crystals of uranium, what they were actually doing was, it meant that the uranium compound was emitting radiation. So it was giving off radiation, just like when it was exposed to light and it gave off this luminescence. What was happening is, even without it getting an external energy source like from the sun, it was still able to give off this radiation just spontaneously. So what he actually had discovered was, he had discovered radioactivity. That's what he had discovered, and he just came across it by chance. So and basically what was happening was, there was just this spontaneous emission of radiation from the nuclei of the uranium compound. So you just got this spontaneous radiation that was coming off. So this was, let's say, this is how radiation got discovered. And after that, so he carried out more experiments. So following experiments after that showed that other uranium compounds, so compounds that contain uranium, as well as like uranium ore, just pure uranium that's dug up, had the same property. So it had the same property of just spontaneously giving off this kind of radiation. So he had discovered radiation. Now what he also noticed as well is, he started to notice that this radiation that was given off, it actually ionized the air. So it turned the air into ions, and it enabled the air to conduct electricity. So it had that, so this, whatever this radiation, they didn't know what it was at the time, it had the ability to ionize the air. So it had an ability to, so if you think about what the air is made up of, it's made up of oxygen, nitrogen, and water vapor. So it was able to smash those atoms apart and create ions, and to the point of where air was actually able to conduct electricity. He also found that the radiation emitted by the uranium compounds could be deflected in the magnetic field. So imagine you have a magnetic field like so, and you have this radiation that's passing through it. When you turn it on, it gets deflected. It gets deflected within this field. So what that meant was that whatever this radiation was, so you had this radiation coming through, it was probably made up of some kind of particles that were charged, or positively and negatively charged, or even both. So that's what that meant by passing it through a magnetic field. So if we think about uranium then, so uranium is the 92nd element on the periodic table, and this is kind of like what the structure of a uranium atom looks like. And you can see within the nucleus here, the nucleus is very, very dense, and you can see that it's quite a heavy atom. So it is. So this nucleus is quite dense, and there's isotopes of uranium. So uranium that has more neutrons, let's say, within the nucleus, that are very, very unstable. And what happens is, they can easily be split apart, and when they're split apart, they release huge amounts of energy. And this is the basis of nuclear power, and also nuclear weapons as well. So if you think about Hiroshima and Nagasaki, so you had roughly like 1 kg, a bag full of sugar of a particular isotope of uranium that was reacted, that caused a nuclear reaction and caused the destruction of, like, basically the obliteration of a whole city. And that's basically that, all of that energy comes from the nucleus of the atom being split apart. So there's huge amounts of energy contained within inside the nucleus of the atom. So this is basically like how radioactivity was discovered. and it was credited to this guy here. So again, what we'll start to do, what I'll look at in the next couple of lessons, we look at some further work that was done by other scientists as well, just in relation to this. But this is just as an introduction to radioactivity, and kind of just to give you a general overview about what radioactivity is. And we'll start to look at it in a little bit more detail. So hope you enjoyed that, and thank you for listening.